everyone, welcome to this Enrisu video podcast. My name is Cyril Noger. I'm a field application engineer in the EMEA region. This presentation will provide you all the information required to understand how a handheld spectrum analyzer is able to decode a 5G new radio frequency carrier on the field to get accurate measurements for the network deployment. The main topic here will be to understand the so-called grid of beam concept that has been implemented by the 3GPP at the same time of defining what 5G signals are. So let's have a look at the different topics we will explore in this podcast. In the first time, we'll have a look at some 3GPP 5G basics to have a better understanding of the few new acronyms introduced by the 5G technology. Then we'll dig into a 5G carrier example to understand more about its frame structure. We'll also explain what the synchronization signal blocks are, where they are embedded in the 5G frame. When this will have been done, we'll have a careful look at the kind of information the SSB are carrying and what they are made for. Finally, to finish with the theory of 3GPP, we'll explain what is meant by grid of beam for a network provider point of view for smartphones to be connected to its network. To illustrate all what have been said in this podcast, we'll illustrate this by a real example using the latest generation of an handheld spectrum analyzer, the MS2090A, which is able to demodulate a 5G carrier and to provide all necessary figures to qualify how good or poor a 5G transmission is. This will be done by seeing a real operation being recorded to decode a 5G signal. As mentioned in this presentation, we will first have a look at the 5G standard and study where this grid of beam is coming from and what it means for a mobile to be connected onto the network. So step by step, we will go from the theory up to the reality on the field, making the link from what 3GPP has defined on the official test specification documents up to the observation of the network behavior being decoded by a high performance spectrum analyzer like the MS2090A. The handheld spectrum analyzer that will be used to illustrate this presentation is the MS2090A. It is the latest generation of field spectrum analyzers on the market with unrivaled performances and revolutionary touchscreen graphical user interface. We will detail a bit later what it is capable of in 5G measurements. So let's first have a look at a few basics on the 5G new radio technology to have a better understanding about what's been introduced and new acronyms. So let's have a look at the new 5G Mineralogy and frame structure. So for instance, you have to know that 5G NR has introduced some new frequency bands like the sub-6 GHz band and the millimeter wave band, which are called FR1 and FR2, and the possibility to get subframe spacing values different. The length of a radio frame will always be 10 milliseconds, so this is good to keep in mind, and the length of a subframe will always be 1 millisecond. Then, depending on the bandwidth of the 5G carrier, different sub-carrier spacing can be used by the network operator. Since 5G is mostly TDD based, what does it mean? It means that the same frequency carrier will be transmitted with both downlink and uplink in the frame. We'll see later in this presentation the consequence of having TDD technology when using a spectrum analyzer to make proper measurements. To simplify the approach to 5G all along this video podcast, we'll take the example of a 5G frame with 30 kHz sub-carrier spacing. We can see from what 3GPP has defined that for a 5G carrier with 30 kHz sub-carrier spacing, the bandwidth could vary between 5 to 100 MHz maximum. So we'll focus on the example of a 100 MHz carrier bandwidth in this presentation. Let's now have a look at the 5G new radio frame structure in more details to get a better understanding. As I've mentioned already, the length of a 5G new radio frame is always 10 milliseconds long, and one frame is always 10 subframes. Each subframe is 1 millisecond long. This frame structure is important to keep in mind as we'll go deeper into this from now on. So the uplink and downlink transmissions are organized into 10 milliseconds framed in TDD in 5G. The subframes are divided into slots, and the number of slots of a subframe can be divided into 1, 2, 4, 8, 16 or 32, and it is depending on the subcarrier spacing that has been chosen by the network operator. Each slot contains 14 symbols when the normal cyclic prefix is being used. And as mentioned before, we will focus on the 30 kHz subcarrier spacing case, which means that one subframe contains 2 slots and each slot is 0.5 milliseconds long, and each of these slots contain 14 symbols. Let's have a look into this subframe structure showing the 2 slots that it contains and their OFDM symbols. In the case of a 30 kHz subcarrier spacing, each slot contains 14 symbols, as I said already, and one resource block consists in that case of 14 symbols and 12 subcarriers, as shown on this slide. Let's represent the frame in 2 axes. The horizontal axis represents the time domain and the vertical axis represents the frequency domain. One 5G new radio frame with 100 MHz and 30 kHz subcarrier spacing means 10 subframes, 20 slots, 273 resource blocks. We'll now describe in this slide where the signaling part could be and the kind of useful information channels it contains. The signaling part is the most important data to be decoded by the 5G smartphone or tablet to understand which cell could provide data. As shown here, the particularity of the 5G carrier is that the signaling part could be located anywhere in the frequency domain inside the carrier. This means that the yellow and orange blocks we see on this drawing can be transmitted as a single block, also called burst, centered onto any frequency inside the carrier. This block is also called SS block, which means synchronization signal block, which is called SSB. And for 5G sub-6 carriers, the SSB will always be contained somewhere in slot 0 and slot 1. This is shown here in blue, and the slot from slot 2 up to slot 9, this will be dedicated to downlink and uplink data, which is shown here in velvet. And in the next slide we'll see what 3GPP has determined in terms of frequency allocation in the frame for this SSB. Synchronization signal blocks are also called global synchronization raster. It is a channel on its own and has a channel value defined by 3GPP specification. The most important information to remember from this slide is the fact that the center frequency of the SS block is defined by the 3GPP channel number, and it is called GSCN. This channel number is converted into a frequency value and it represents the frequency of the SS block. The position of the SSB center frequency can be expressed as a relative offset compared to the center frequency of the 5G carrier. On this current slide we show SS block located at a lower frequency compared to the center frequency of the 5G carrier on its own. If we try to illustrate the example of a negative relative SSB offset frequency compared to the center frequency of the 5G carrier, it could be represented as shown here. The SS block would be located before the middle of the radio frame. To make this assumption clearer, here are 4 examples showing different possible position of the SSB within the 5G carrier. Every time the position of the center frequency of the SSB is expressed as a frequency offset. If the SSB center frequency is located below the center frequency of the 5G carrier, the offset will be negative. If the SSB center frequency is located above the center frequency of the 5G carrier, the offset will be positive. If the SSB center frequency is the same as the center frequency of the 5G carrier, then the offset is 0 Hz. Now comes the time of getting more complex information in mind, but this will be summarized here with this table coming from 3GPP test specification 13.213, which describes the existing subcarrier spacing values depending on if the 5G carrier is in FR1 or FR2, and It details the maximum number of SSBs and their representative starting symbol position in the frame. The UE has to find the starting symbol of this SS block, then to decode the synchronization signals contained in the SSB when searching for the cell. The Lmax is a parameter which defines the maximum number of SS or physical broadcast blocks in the frame. This value is determined by subcarrier spacing and frequency range. And as already mentioned, we will focus on this 30 kHz subcarrier spacing case, which is also called case C by 3GPP. As I've just mentioned on the previous slide that the SSB has predefined starting symbols in the radio frame, the current table you see here allows to draw the frame graph below the table if we want to understand more. We can see the starting position of each OFDF symbol of each SS block. The case C described here highlights the fact that the 8 SSB maximum can exist and transmitted in the frame. As shown here, these 8 SSB are transmitted in subframe 0 and subframe 1. Let's have a look at the synchronization signal block more in depth. Since we use the example of a sub 6 GHz band carrier having 30 kHz subcarrier spacing, the previous slide has shown that there are potentially 8 SS blocks that can be transmitted. These are highlighted here in velvet, and we can see the different channels that they contain. A SS block consists of 240 contiguous subcarriers, which also equals to 20 resource blocks. This can be seen on the vertical axis here. These subcarriers are numbered in increasing order from 0 to 239 within the SS block. Each SS block transport signals like PSS, which is the primary synchronization signal, SSS, secondary synchronization signal, and PBCH, physical broadcast channel. The PSS and SSS are 127 subcarriers long, and the duration of a SS block is 4 OFDM symbol. On the right side of the slide, we can better see these channels inside a signal SS block. This 3GPP figure shows the frequency versus time structure of the synchronization signal and the PBCH block. The synchronization signals in the SSB consist of primary and secondary synchronization signals, also called PSS and SSS, each of them occupying 1 symbol and 127 subcarriers, and the PBCH spanning across 3 OFDF symbol and 240 subcarriers. The 3GPP TS 38.213 and section 4.1 is focused onto the cell search mechanism. It defines where the first OFDS symbol number is for the SS and PBCH and to be transmitted in the frame. The smallest element, small square that you can see here in the graph, is also called resource element. The UE may assume that the resource element denoted as set to 0 are not used. So how is the SSB index to get informed to the UE? Each SS block within the SS block set is assigned with a unique starting number from 0 and increasing by a step of 1. This number is reset to 0 in each SS block set, which means next 5 millisecond span after SSB has been transmitted, and by default SSB can be transmitted every 20 milliseconds. The periodicity of the SS block can be configured by the network operator, and the time locations where SSB can be sent are determined by the subcarrier spacing. With the frequency span of the carrier, multiple SSB can be transmitted. Physical cell IDs of those SSB do not have to be unique, and for instance, there are different SSBs can have different PCIs. As a summary, we can say that the SS burst is sent over a duration of 5 milliseconds, which is a half frame long. This burst contains one or more signal blocks, so there may be just one SSB or 4 or 8 in FR1, and they occupy a maximum period of 5 milliseconds. The maximum repeat rate at which SSB could be sent could be every 5 milliseconds. There is a higher layer network parameter called SSB Periodicity serving cell, which informs the UE about the SSB periodicity being used in the cell. If this parameter is not used or not known, then the UE may assume the value is every 2 frames, which means every 20 milliseconds, as this is the default value. So 20 milliseconds becomes the default value of the SSB bursts. The actual value of the SSB periodicity serving cell can be 5 milliseconds, 10, 20, 40, 80 or 160 milliseconds, and this is given by 3GPP TS 36.331. This can be chosen by the network operator when they configure the network, assuming the base station, also called G-Node B, is supporting all the modes. In the cell search mechanism, the PSS, SSS and PBCH help the UE to synchronize onto the G-Node B. If the UE manages to decode the PSS and SSS, then it is able to calculate the value of the cell ID, also called physical cell ID or PCI. The PBCH also carries important information that are used by the UE when establishing the communication within the network. As mentioned, the cell search is the procedure by which a UE acquires time and frequency synchronization with a cell and detects the cell ID of that cell. The new radio cell search is based on the primary and secondary synchronization signals, PSS and SSS, and the PBCH-DMRS, which is located in the synchronization raster we've already spoken about. Once the PSS and SSS are known, it becomes easy to calculate the cell ID as shown here with a formula. As the SSB not only contains the PSS and SSS, it is also important to decode the physical broadcast channel. As shown here, the PBCH reference channel is one other important metric to be measured to be able to understand about the quality of the transmission of the 5G carrier. The PBCH-DMRS is represented here in brown and is located at specific resource elements positioned inside the SSB. Now comes the concept of the grid of beam, which is a crucial topic to be understood to emphasize one of the differences between 5G and the previous cellular technologies. In 5G, the coverage is beam-based, it is not cell-based. So what is a beam then? The 5G radio coverage doesn't work the same way if we would have to compare the two previous cellular technologies like 2G, 3G or LTE. There is no cell level reference channel from where the coverage of the cell could be measured. So instead of that, each cell has one or multiple synchronization signal block beams. These beams are static, semi-static, always pointing at the same direction. They form a grid of beams covering the whole cell area. The UE searches for and measures the beams, maintaining a set of candidate beams to establish a communication with the network. The candidate set of beams may contain beams from multiple cells. The different SSBs or beams of a cell are transmitted at different times. Therefore, there is no intra-cell interference among the SSB beams, and at least the scanning receivers should be able to detect also extremely weak SSB beams, even in presence of a dominant, strong beam from the same cell. This slide tries to simply show the main difference between the RF coverage in LTE and 5G. Thanks to the usage of the SSBs and potentially the beamforming mechanism, the RF coverage could be enhanced and it becomes more efficient as seen by the UE. We'll come into more details in the next slide. The grid of beam introduces a new notion which is called beam sweeping. So what is it? Beam sweeping by the SSB. Multiple SSBs are transmitted with a certain interval. Each SSB can be identified by a unique number called SSB Index. Each SSB is transmitted by a specific beam radiated in a certain direction. Multiple UEs are located at various places around the node P, and each UE measures the signal strength of each SSB it detects for a certain period of time. As shown here, if we consider a 5G new radio carrier potentially with 8 SS blocks, this means that the cellular network would transmit the data via 8 beams from the active antenna system. This is called the grid of beams. How many different beams are transmitted and determined by how many SSBs are being transmitted within a SS burst. As we've already explained in the previous slide, the parameter defining the maximum number of SSBs within an SSB set is called Lmax, as from 3GPP. In the sub-6 GHz band, Lmax is 4 or 8, and in the millimeter wave band, Lmax is 64. In other words, in the sub-6 GHz band, max 4 or 8 different beams can be used, and they sweep in one dimension, or horizontally only or vertical only. In the millimeter wave, 64 different beams maximum can be used, and they can sweep in 2 dimensions, horizontal and vertical directions. The illustration of the SSB transmission shown here is the case where all SSBs are transmitted, but it is not required to transmit all the SSBs, and depending on the network requirement, it can selectively transmit only a few SSB and inform the UE of which SSBs are transmitted and which are not transmitted. In our current example, we focus on 2D sub-6 GHz and Lmax 8, also called case C, which means that 8 SSBs maximum can be transmitted in 2 milliseconds, as shown on the graph on the top. As I've mentioned, the SSB beams are static or semi-static, always pointing to the same direction. All beams are pointing in a different direction. They all form a grid of beam which covers the cell area. And on this slide, we can represent for a sub-6 GHz carrier with 30 kHz sub-carrier spacing up to 8 beams being transmitted from the same antenna on top of the antenna tower. We now know that each SSB is identified by a unique number called SSB Index. Each SSB is transmitted via a specific beam radiated in a certain direction. Multiple UEs are located at various places around a G node B. UE measures the signal strength of each SSB it detects for a certain period, which is called SSB set. From the measurement results, UE can identify the SSB index with the strongest signal strength. This SSB with the strongest signal strength is the best beam for the UE1. For instance, this is beam number 1, and for the UE number 2, it is seeing the beam number 7, which is the strongest one. If the MS2090A spectrum analyzer or the UE were located in the middle of the cell covered by one antenna transmitting 8 beams, the MS2090A or the UE would likely see more power on the beam 4 and 3. This kind of bar graph display will be used by the MS2090A unit on the field to know more in details about the presence of SS blocks in the 5G carrier and the quality of each of them. As SS blocks are the first items to be decoded when being on the field, let's see how a UE or a spectrum analyzer like the MS2090A is able to quantify and the quality of the transmission it is getting at a given location in the cell. In field measurements, the metrics contained in the SS blocks, PSS, SSS and PBCH, can be collected both with scanning receivers and test UEs. Hence, SSB beams show up as a kind of new layer of mini cells inside each cell in the field measurements. In terms of measurements, 3 parameters can be evaluated: the RSRP, the RSRQ, and the SINR. Let's quickly see on the next slide how these are measured. This slide shows how basically these 3 metrics are calculated by the UE or the MS2090A once the 5G frame is decoded and the SS block are found in the frame. The RSRP focuses onto the power of the SSS for each individual SS block. The RSRQ is a ratio measurement that compares the power in the reference signals, the RSRP for instance, against the average power of the physical channel, RSSI. The SINR allows to estimate the transmission quality of the channel. It can somehow be associated to the EVM, error vector magnitude. Now that the concept of beams and synchronization signal blocks has better been understood, let's focus onto the measurements a high-performance spectrum analyzer like the MS2090A can provide when demodulating a 5G carrier. The MS2090A is the latest generation platform of handheld spectrum analyzer, and it has been designed to match and comply with the test requirements of the 5G carriers. The MS2090A is being used by network operators to troubleshoot the installation of the network to ensure that they will be able to deliver the best service that they can when the network will officially be launched. The 5G technology deployment is a kind of new challenge, since 5G is really different compared to the previous cellular technologies. New measurements are to be learned by RF technicians and engineers, and the MS2090A is there to simplify their daily life and making proper measurements complying with 3GPP. In the 5G NR measurement software of the MS2090A, if all parameters are correctly set, the center frequency, the subcarrier spacing, the bandwidth, the offset value and the amplitude, it is possible to demodulate the 5G carrier. And with the 5G example we have here, we can see that 8 SSBs are being decoded, and these are the blue vertical bars that you see on the screen. And below each of them are the metrics of the SSBs, RSRP, RSRQ, and SINR. On top of the screen, called multi-beam view, we can also see that the physical cell ID is being decoded and displayed, which is in that case 107, including its sector ID and cell group ID. The MS2090 also measures the frequency error of the 5G carrier. If the user wants to focus onto a special beam, he just has to press on single beam button on top of the screen to get more information about this beam. Now we can see, for instance, that for beam 6, the EVM measurements of the PSS, SSS, PBCH, PBCH-DMRS, and all the measurements are refreshed in less than 2 seconds. To conclude this video podcast and to let you understand how to operate in reality with the MS2090A spectrum analyzer, let's have a look at a short recorded video where, from a preset state, the MS2090A has to be configured to decode the 5G carrier. So from the spectrum we go to the 5G option, and we have to configure the frequency as I already mentioned. So let's focus onto the 3.65 GHz frequency. Then we have to set the SSB offset as long as it is known. So in that case, minus 12.96 MHz, and then wait for a few seconds to synchronize and decode the beams. So now we have 8 beams apparently on the screen. Since we are in sub 6 gig band, we can adjust the level, get the multi-beam view full screen on the display, having a look at the RSRP, RSRQ, SINR of each beam, and then focus on single beam measurements to get access to the PSS, SSS, PBCH, EVM measurements. This is quite straightforward indeed. We are now at the end of this presentation, dealing with the understanding and interpretation of the synchronization signal blocks contained in a 5G new radio carrier that can be measured by a spectrum analyzer like the MS2090A. So thanks for your attention. If you require more information, please do not hesitate to contact us and to visit our website www.enrichsu.com.